Shall we start? Everyone able to hear me?
Yes.
Cool. Now, I forgot what intro she gave me, so I'm going to reintroduce myself. My name is Darshan. I'm a solution consultant here at Sahaj. I've been working in mostly the data engineering space over the last 2 to 3 years. So I've spent most of that time working with Spark and a couple of other data. Now, better was most of my time in Spark is spent on cloud support. So I had to learn a lot of things about internet in Spark as well as the performance implications of it, and also how you can kind of make it cost effective. So those are some of the things we're going to talk about today. So in order to get there, this is your right. So to get there, there's a lot of the fundamentals about DB that we'll be covering. Just a few slides before we get to the meat of it. Can I quickly do a sense check? How many of you have heard of DB before? Okay, cool. So a lot of you, this is first time. Okay? So I think data science is a term a lot of people tend to confuse with data engineering. So I think that where the difference comes in is data engineering is about building full-fledged systems, like production systems, which can kind of help you collect data. Now, any typical enterprise, right, you have once you operate at sufficiently large scales, you're going to be getting data from all over the world. Some data is things that might come from your own applications, from various teams within your company, different products that you might have. And also you start receiving data from other sources, which can help improve your own business insights. Now, how do you combine all those data sets together to get something actionable? Now, that's kind of the core of data engineering. That's kind of their aim to get the whole thing out. Okay. So in order to do this, I've covered everything on stage. So yeah, some of the various actions that are involved in data engineering, they are about collecting data from different sources and being able to clean them up, sanitize them, basically make them ready for whatever other things you may want to do. That could be training and running models. It could be serving other backend applications, cleaning sites, anything of that sort. And it is also about generating daily reports and other statistics that your business may want or your end users may want to see, all based on new data. Right? The reason they can be challenging sometimes is because a lot of these things that we do, they need to repeat. They're not one-time scripts that you run and be done with it. If you generate reports or want to train models, you will have to redo it every day or every week as and when new data comes in. And it's not like your business is going to say, forget the old data. You'll say, I want the old data and the new data. So your scale at which you operate is going to constantly grow. But your hardware costs can't. The business wants more data, you don't want to pay more money. Okay. So you have to be very cost effective and performant while calculating your insights and other things. So that's the core ask of data engineering. Now, these things that I just spoke about, anyone wonder why I can't just do this in Postgres or any other database? Sorry, what was that? Not distributed. Why does it need to be distributed? So if I remember correctly, the biggest instance that AWS gives you for Arch Postgres is about 1 terabyte of RAM, and disk is in favor of 1 terabyte of RAM. So any calculations, any reports, anything that you want to generate, it's going to talk about that 1 terabyte of working memory until what RAM comes in. So that's one. But there's actually a couple more reasons. So we spoke about our data volumes constantly growing. So a typical scale, right? think about a company which has to process maybe 50 terabytes of data in a single report. Now, 50 TBs happens to be a random number, but it's very realistic. A lot of companies actually have to do a lot higher than that. So let's say you have 50 TB of data stored in some disk. It is like it's stored in disk, but you have to retrieve it and perform your calculations on. So how big a machine are you going to need? You're going to need severe CPU power and RAM. Okay? And how long is that query going to take? If I have a single SQL query, it's going to take its own speed time. We don't want the user sitting and waiting for that long. So those are some of the reasons data is getting upset. So there are use cases for Postgres as well in the DB ecosystem. We'll talk about it in the upcoming slide. There's some stuff about business use cases. But one of the main driving forces in DB is to have stuff running as a background process. So compute is not cheap. Right? If Postgres takes time, other platforms are also going to take time. Might take less time, but it is still time that you don't want users to see. So a lot of DE tasks actually are async, which Postgres is not very well suited. And yeah, that's the other thing. If things are async and batch operated, you don't want very heavy Postgres or actually any database. You don't want it running 24/7. You're going to run batches. But if it's Postgres, you also can't kill it. Right? You still have to pay for it and keep it running. Otherwise, you lose all your data and you have to import everything again. This is another practice. So, good DE lectures. So, coming to building the pipelines in production, it's a lot of the trade-offs that you make when writing normal platform code, they tend to translate over to the DB ecosystem as well. Everyone is comfortable with object-oriented programming. Yes. Are you comfortable with classes that are thousands of lines long? So the same thing kind of applies here as well. We'll have real world use cases in a little bit, but core of it is that if you want to build very large pipelines or very large jobs that have to talk to 3 or 4 different data sets and combine them, it is generally not a good idea to have all of it in a single job, because if you can make things smaller, you get kind of building blocks. As the business grows, that's what like new reports, new analytics, support other use cases. You'll be able to build on top of what you already have if they are small and usable. You can't do that if the whole thing is one single job. You have to rewrite it. And yeah, that also helps you reach market faster when you want to build something more. Because half the work is already done. And the other, my favorite, I mentioned it, I'm a big fan of anything that makes plots and book easier. So if I have a very large job and it happens to fail in the middle for any reason, I have to retry it. Let's say that thing took 6 hours to run. That's another 6 hours I have to wait. But what if I broke it into 6 jobs, each 1 hour? It's not all going to fail, right? It fails somewhere halfway. At least I have a checkpoint. 3 hours is done. I just have to do the remaining 3 jobs. Okay? It makes life a lot easier. Any questions to you? No? Okay. Moving to the next point. Keep data sets immutable. Anyone knows what immutability is? Anyone who does it? Good. So basically, you write a data set once and you don't change it. You keep the same data as it is on disk. Once something is calculated, save to disk, you never touch it again. And you can read it, you're not allowed to overwrite. That's what immutability means. And the power that gives you is history. This image on the right actually talks about the same thing. So imagine you have some kind of job which runs every day or every week. Once it finishes its calculation, you would want to write it to a new location on your disk. This is what the year 2020 month 1 day 1 signifies. The reason you do that is the minute you have a new folder, you can simply move your downstream pipelines to start reading the next folder, and you don't lose your old data. Right? So in the event of, let's say, this news of having a maybe the input data was wrong, and you realize, well, I shouldn't be using this data in production for any reason. I have something I can roll back. That's one. Second is legal reasons and audit trails. Okay? There's a lot of times people will come and say, why did you report something to me? Or what gave you the confidence to say this particular intelligence was true? And they can come to you and ask this 2, 3 years down the line. Okay? Depending on how far away the business wants it, it's always a good idea to keep all your previous data sets available in place. And the cost is also pretty low. Some of you might have heard this storage versus compute, the cost difference. You have. Basically, compute is like 10 times more expensive than storage. That's the average. So recalculating a data set when you need it is always going to be more expensive than simply keeping it in some storage or somewhere. And these days, storage is even cheaper. S3 and other days, they have like really competitive archival storage. So you can save like petabytes of data and pay just a few dollars. Okay? So that's one of the fundamentals in data engineering. Right? You keep everything immutable. And the next one, which I already spoke about earlier, anything which takes significant amount of time to run, anything which is expensive, you don't want it to run in real time. Right? Whether you use Spark or Hadoop or even plain Postgres, it's something that's going to take more than a few seconds, easily more than a few minutes. Right? So you don't want something to be waiting there. You want it ready to run. So if there are any insights or like a recommendation that you want to give it, you don't want to do it when the user comes and asks for it. You want to look at your historical data, calculate what recommendations you want to give, keep it ready. And then when are the users ready, this what you've already computed. And this, by the way, is a use case for a database like Postgres that I was talking about. Once the expensive calculations are done and your reports are ready, you can save it somewhere in a database or anywhere else that lets a user quickly get it. So far, so good. Any questions? No? Okay. The last bit that I want to talk about is map radius. Anyone knows what map radius is? Yeah. 2 people heard about it. Amazing. Yeah. So the reason I'm talking about this is because it's important to know the context in which the Spark framework came into play. And this was about 2012 when Spark was first launched. And at that time, MapReduce was the industry standard. It was as popular as Google is for searching. You want data engineering, you have to go to MapReduce. That's like the gold standard. And yet somehow Spark came out on top of that, did what nobody else could. They beat MapReduce. They gained popularity so much that now Spark has the market share in MapReduce. Okay. Now, how did it get so popular? Because there are few limitations that we will talk about. And it's important to know these limitations because they affect how we write our Spark code. So, quickly talking through MapReduce. This is an example for word count. It's like a standard example on the MapReduce website. Yeah, I stole this picture from somewhere. So imagine you have a big set of documents with sentences. You want to do a word count. You want to figure out which words occur how many times. Nice, easy problem, right? The way MapReduce does it is, you read one document at a time. Imagine each line is its own file. Okay, so that's its own data set. So you read all of them. That's the splitting action here. Right? You split each line into its own partition, and then you apply the mapping logic. So each sentence gets mapped to like a tuple after it got split into words, and now you have a count. And you can see each box has individually split into 3 more. Now that's the mapping stage. Each word has some count associated with it. Now you have to get to the reduce stage. Reduce is when the actual count happens. Basically, you look at the data across 3 or how many boxes you have at this point, and you merge all of the ones with a similar key together. So you can see from this box, arrows going all over the place, and they've all become like the same words showing up in the same boxes. Okay. And once that's done, the reduce state. That's a very simple operation. You iterate through all of them, use sum of the keys. That's your answer. Last one is to concatenate. Some smart people might have noticed I just lost over this stage, the submit stage. That's because this is the, how do I put it? It's like the bane of any data engineer's existence. The only way you can go from here to there is if you transfer data across all of your boxes, right? In this case, you need to basically go through each box here, figure out which data is sitting there, and then send it from here to there. Now, here and there are two separate computers, right? All of this is distributed. Someone is saying, no, one of the reasons for D to come in and replace Postgres is because you want horizontal scalability. You want distributed computers. It's not happening on one thing. So in theory, each of these boxes is sitting on a different computer. And each box is going to be several gigabytes in size. So you have to actually transfer all the data from here to there. This is usually the most expensive stage in any data engineering job. So that's it. This is your the base MapReduce logic. Now, going forward, quickly we're going to look at code, also for MapReduce, also stored problems. So I just a small snapshot of what it does. I'm not going to go through it because the focus today is Spark, not MapReduce. So you basically get each document in your parameters and you have to read through it, you have to figure out how you want to break it. And there's a little thing called context. That's the stage where you break it into pieces. So you basically read a document, each piece that you want to get out, you write the context. That's how you expand the number of documents. And reduce just gets the list of values. It's a list here because it's a tuple. So you can see both values here, and again you get the context. And this guy is MapReduce will ensure that the iterables are all for the same key, which was the left center. Once you get all that, you perform whatever operation you want. In our case, it's a sum. You write that out to the end. So this results in this box getting created. MapReduce will take care of merging all these boxes, saving it into one document for it. So far so good. So I have a question. Everyone here is comfortable with SQL? Yes. Awesome. Tell me, would you prefer to write code like this, or would you prefer to write text to do the same operation, work on it? SQL. Any Java expert says yours is better. Now, I do think this has its use case. Please don't think I just say bad things about MapReduce. That's not the case. But in this case, right, SQL is going to be a lot better. Now, think about a slightly bigger use case. This is more enterprising. It's a completely made up example, but it's more case. So, introducing playfix. I'm sure everybody knows what that's a synonym for. So imagine that they have their own set of data. Like we said, every enterprise has their own data, plus they want to tie it with something else. So in the case of someone who's a big OTT platform, what kind of data sets would they own? They're going to have a big set of movies. Okay? They're going to have data about their own movies. They're going to have data about all their users, like what kind of things they watched. Out of everything they watched, what did they like? Right? And of course, if they have a recommendation engine, they're going to know what movies I recommended to them in the past. Now, this is their own data. If you were a business and you wanted to make your recommendations better, meaning you want to recommend something that the user is going to see and fall in love with, right? That's how you keep your users engaged. How do you do that? It's your own data. So, in this hypothetical world where privacy is not a thing, you can actually imagine that you get data of all of your users' web searches. Right? Someone Google's Rajnikant, you know you have to recommend all of his movies. Someone likes a post on FB, Facebook about anything. It could be about a thriller book or something else. You see that data and you know, okay, this is something I feed into my model. Same way it applies to watch history or YouTube. Now, thing to note here, all three of these came from different companies. All three of the data, they're going to have their own schemas. Actually, seven, 4 plus 3, 7. All of them is going to have very different schema, different set of data, blah, blah, blah. Now, you take this data and you give me a new movie recommendation. I want something that runs top across all of these and is not present in my past recommendations. You need to recommend something new. Can we write an estimate query for this? No, that is more realistic. It is possible, it's not very nice. Now, nobody wants to write SQL. Would you like to write this code? Oh, really, it's better. Okay. You want to take that as a challenge? So, moving on, right? Well, this probably seems simpler, but that's because it's map reduced. Imagine how many of sorry, this is word copies not. How many of these would you have to write to get here? Right? You're going to need jobs to sort of get the list of movies, break it into genres, club it with your watch history, then clean up all of these, club it all together, and then finally do some sort of a merge and order by priority, get out recommendations. It's making up values here, it should be. But can you write all of that in one of these? No. Going back to the fundamentals we spoke about, you do not want to write a single job which does all that. You want to find a way to break it into smaller jobs and then do everything. Right? Now, even within the smaller job, imagine you had to do a list of movies, club it with web searches. So web searches, imagine they search very simple, right? They search for thrillers, Tamil, basically genres of movies. And you have a list of movies which has this. Now you want to search for that, again you want to prioritize within that. Right? If I search for the same genre repeatedly, I want it to show up on top. If I just randomly did a search somewhere, it should rank lower. Would you do that in a single job? I would. But can I do it here without treating myself? It's going to be a little harder for myself. So this kind of brings us to the various limitations in marketing. By the way, everyone agrees with what I said so far. Anyone want to have a part in it? I can't understand why it is. Why? What is it? Why do you say it's because what how prioritize how it's on the number of times I get the website on that on why is it it will run it absolutely will run, but it's about your own experience. For word count, people said you prefer to write SQL over Java code like this. Does that apply to the job you just described? I would I prefer. Yeah. So some of the issues here is with this little thing of context, right? And the format it operates in. We have a few more limitations actually. Developed experience is not the only one. But the challenge here is the tuple structure. Right? You kind of have to ensure that your input data is mappable and it has to go here. And after that, you need to stuff all of your logic which operates on the same key. Now, what if you can't get a single key? We spoke about what was it? Search history and movies, right? What if it's a composite? It's still doable. MapReduce is very flexible. You can have even tuples as a single key. But that is how your complexity goes up. If you don't want to have to do all of it in a single Java function, if you want some more flexibility. And most of the time, simply writing an SQL query is going to be more concise and real than this one. At least that's my claim. Uh, yeah. So as you said, yeah, cool. So some of the limitations that we've spoken about. One of the biggest things is that in your pipeline you can do exactly one map operation, exactly one reduce. It will have only two of those functions. And if you want to club 4 or 5 different data sets like we just spoke about, it's not going to happen. You have to either do it all in a single function or somehow break it down into linear steps. So that's one limitation. It's a little harder for us to think about it. And having something linear, does that have any performance implications? So I cannot proceed with the next stage of my pipeline until the first one is completed. And in order for it to be complete, we spoke about the entire map reduce flow, right? So it has to actually read data from disk, has to do all this magic, finish whatever map operation you had, finish the shuffle, do the reduce, write everything to disk. All of that for just stage one of the job, the first map reduce. Rinse and repeat all over again, right, for the next step. Now all of this is an overhead. What you really care about is simply map and reduce. Everything in the middle is an extra performance hit that you are taking. Okay? So that's one of the issues with the linear flow. You can't parallelize anything, you have to run it all together and you have to write everything to this. Writing to this column, is it's not as fast as doing things in memory, right? If you want something that's running on disk right now to become faster, what's the first thing you do? You move into memory. So yeah, that's one. And the second thing is eager evaluation. Taking the word count example again, you have a set of words. Let's say they are all in random case, some lowercase, some uppercase, blah blah blah. Now, if you want to word count, you don't want to consider others, you want to ignore them. So what do? You will first read the whole data set, you will capitalize it, keep it, and then you will perform the same operation as before. We've now talked about two different map operations. If you wrote it as two map reduce jobs, now you have the whole flow happening twice. But I don't actually need to calculate the uppercase and save it to this. I need it purely forward count. So what if I calculated it, kept in memory, did the next thing? Not. Job will be a lot faster. That's not possible with MapReduce. You have to take all the intermediate jobs and store it on disk. Okay. So far so good. Any questions? Cool. So what I spoke about is like the base. This is the situation the ecosystem was in at the time Spark came into the picture. Okay. Now Spark actually grew up in a lab, in a research lab at some big company, not a company, a big university, or what they mean, sorry. So they actually did all of this. They figured out these are the limitations, and then Spark came in. That's why adoption rate was so much higher because it solves all of the pain points that we just spoke about. How does that happen? First thing, lazy evaluation. That's the case I just spoke about, right? With the capital expense. You read once, you process it. You don't need to evaluate the capitalize until you're ready to do the count. You can just do it in one pass through the data. You don't have to read it, write it, then read again. So that itself is a big time saver in Spark. And the second new choice Spark made was to keep everything in memory. So between MapReduce coming out and Spark coming out, there's like a 10+ year gap. At that time, with MapReduce, memory was quite limited. Processing such big things in memory was simply not a thing. But now hardware is there. Right? You have 16, 32 GB of RAM. 16 is like the base these days. Right? It's enough to store and process 10 times more than what MapReduce could have at that time could have done in memory. So at this point, it's now feasible to do all operations in memory. So that's one of the things that Spark does. There are no operations happening on disk. Everything is in memory. And the third thing, which is about caching and reusing data. We just spoke about the whole capitalized being saved. Now that's a very small example, but you could be doing a lot of more heavy operations. You could be joining with large data sets, which you want to use in few other jobs. I actually have a story about that same case. Yeah, I can talk about it actually. Um, but yeah, that places like that, you can actually do the word processing and they're using the same Spark cluster. It will stay in memory. So the next job can reuse it. So these are kind of the things that Spark does. And on top of that, it's fully SQL applied. So it's not Java code in terms of macros, it is SQL that all of us know and are comfortable with. It doesn't mean I write pure SQL. It does have bindings in all the languages, and in fact, that's a recommended way to write Spark. You write code in a language of your choice, which Spark will compile to SQL. We'll talk more about that in a few minutes. Um, so, how does lazy evaluation happen? So, at this point, I hope it's clear. Lazy evaluation is like the core good thing about Spark. It's what enables its big performance jumps. And that's why, as developers, we need to know its strengths and its limitations very clearly. So, quick question: has anyone seen anything like this before? Anyone have experience writing Spark code or using Spark? One person. Three. Four. Okay. So for everybody else, the way Spark works is once you write your queries and your SQL or your Java code, it basically goes through your whole code and it comes up with a execution plan, right? And that this screenshot here is a little subsection of a plan. This is actually the plan for workout. So I have a code for Spark workout on my machine. I run it. This is a plan integrated. It's cut a little bit, but what I'm trying to get to is that it follows a big set of operations. And this is what is known as a DAG, or directed acyclic graph. So each of these is one operation. The fun thing here, right, within this one block, you've got one, two, three operations. The reason there's a filter is because I have added a little something into my word count just to make it clearer. But all of these, because they are lazy, it means I can do the whole thing inside one block. It means, let's say I have to read a sentence from this, I have to split it, I have to capitalize it, and I have to set it down. That's three operations, MapReduce would have done it three times, but because it's lazily evaluated, I can club all of them together. I can read the sentence once, split it, capitalize it, all in one shot, and then send it downstream. And that's what this block recommends, right? I mean, that's what this block says. Everything here is a single stage, and all of it happens once. Now, the great thing here, like I said, no matter how you write the code, it's not fully true, but basically what it means is you can write SQL queries in Spark, or you can write the code in Scala, Python, anything, right? The code is going to lead to the same data, as long as we did not fall into some of the pitfalls, we'll talk about it. But how that happens is because of SQL compilers. Spark, as itself, understands exactly one language, which is SQL. You write SQL queries, it will figure out the best way to evaluate them and do its thing. And the second bit, how does it know what's lazy and what's not? So let's extend that workout example a little bit more. You capitalize something. Now let's say you want to combine it with, let's say, the meanings in a dictionary. So you have one big file, which is a frequency of words, and you have another data set, which is word English meaning, right, from the dictionary. How do you get both of those together? You join the tables. In this case, data types. You join them together. Now, is that possible as a lazy evaluation? I mean, it is very good to join, and but it won't merge here because in order to do a join, you need to know what data is sitting somewhere else. And we spoke about that in the shuffle stage, right? If you have joined on a primary key, you will basically need the data which matches that key, all sitting in the same block. So you need something like a shuffle operation. And this is one of the cases where Spark will say, no, this is the end of whatever lazy operations you've done. Before you move to the next, I have to sort of park it, redo all of it. And that is one of the things we need to be careful about when building that. It's these blank spaces. These are actually called as stages in Spark terminology. Each of these outer blue blocks is a stage. Everything inside them is a task, it's a transformation. So when writing code, we should be careful that as many operations as possible fit into the same stage. That's how you can optimize it.
Each stage have own data or the evaluation on in memory.
Yes. All Spark operations happen in memory. But
I'm asking in between two stages. Are they in memory or they
great question. So we spoke about shuffling, right? What he's asking about is basically a shuffle operation. Once you have data here, and you have to move it to the next uh, node so that you can start the second stage. So every difference, I mean, every time you move from stage 1 to stage 2, it involves a data shuffle. It will mean you have to copy data from here to there. And the question he's asking is, can I keep it all in memory? The simple answer is it depends how much memory your cluster has. So if your cluster has so much memory that it can accommodate the entire data set, then yes, it's going to stay all in memory. But that's not guaranteed. If let's say I'm processing a 50 terabyte data set, do I need 50 terabytes of RAM? Sincerely, would not. So Spark is in a way where even if you're giving it just, let's say, 4 GB of RAM, 16 GB of RAM, it can actually do what we're talking about. But obviously, it can't fit everything in memory. So some of it will spill over to disk. So that's Spark's default behavior, but it's active only in the case of shuffling and caching. Right? If there is some data it doesn't need immediately, it's like a parking spot. If memory is full, it will go to disk. But calculations, all evaluations, they happen purely in memory. Okay.
allows for defining the stages. Stages are
Stages are implicitly defined, but implicit on the basis of the code rewrite. So if see, it's basically like a compiler, right? Any compiler, you give it some language or some code, it's going to compile it into something that it understands. So how does Spark know where the stage is now? It's by looking at your own code, right? Your code translates to a tag. That tag tells Spark where the stage is now.
how will it decide how many nodes are
How many?
in the DAG node? Some nodes will be part of one stage. So how is it deciding that okay, 4 nodes will be part of this?
So in Spark, it's not that some nodes in your cluster will go to staging series. See, the whole point of this tag is that it is linear. Right? Even in this, I cannot go to the filter stage unless I've completed this, unless I've read all the files into memory. So
I tried to ask you, so here is the state, there are 3 nodes. So it could be that it could be 2 nodes.
So right. So can you hold on to that question till we get to some code? I think I might be able to answer this question. Yeah, so pretty similar to actually the next page of your question. How does Spark know what is lazy? What can be merged together? By looking at your code and the changes you're making, it clubs them into 2 pieces. They call actions and transformations. So basically, any operation you do in Spark fits into one of these 2 categories. Okay, we're going to talk about transformations first. So a transformation is something where you give the Spark data frame, which has some level of data in it, and you say you want to do some simple operation on it. I have given a few examples. By the way, I won't be talking about what each of these functions do. If anyone wants me to, just raise a hand or something. But the base one, right, to select a few columns or do a little filter or even join, right, or add in a new column. All of these are transformations. It takes one data frame, it runs an operation, it produces another data frame. But that is where it ends. It simply creates an object in memory which says, these changes are being made to it. It doesn't actually do them. Okay? And this is part of the answer to your question. When it sees something like this, it knows, okay, I'm still in the same stage, I should add another operation. And everything here is evaluated lazily. But when does lazy evaluation get triggered? It gets triggered when it sees something called an action. These are the other operations. So obviously, the bare last time at which you can evaluate is when you actually want to see the final results in your case. That's when you are writing the output onto disk, or when you are trying to see it on your terminal. Or this is a bit of an exchange actually. A lot of people don't realize this, but if you want to do a count on a data frame, that's an action. It's an action because it will print out the value right there on your screen as a number. Everything else, their functions that take a data frame, give you another data frame. Count is an integer. It doesn't fit into that definition. So if you call dot count anywhere in your Spark code, it's going to pause whatever it is doing, end the whole chain, evaluate everything so that it can give you that number. Okay. So sometimes the bugs you see, not bugs, the increase in performance runtime, job runtime, is because there's some count in the middle which people need for some kind of logic, right? Like a group by or anything else. So, did I answer your question? Some extent.
So at the end of every action, the state will come.
Yes. Definitely between actions, there's going to be new stages. That's guaranteed. But sometimes even transformations will result in stages being created. But that won't happen in lazy evaluation. Like, at this point, it's simply going to make a lineage say, I have data frame A, I have B. Now I've joined them to create data frame C. C involves a join in the middle. It knows that much. Okay? But if I'm actually going to evaluate it and I'm going to read it, going back to this shuffle example, I can't join documents on it unless I have all the documents in the same place. That's not guaranteed to happen when I read the input data. It has to be me, the cluster doing it. So it's going to force a shuffle. Anything which forces a shuffle creates a new stage. Because I said that is where the diff lies. Between stages, all one big operation. The point at which you say, no, I can't do this by myself. I have to get something from another. That's where another stage comes in. So there are actually two ways to create these stages. One is actions, another is transformations that are not working by themselves. Now, hopefully the next slide talks a little bit more about tests. Yeah, so we said that there are two types of transformations, some which work in the same state, some which don't. The difference, the technical terms for them are narrow and wide dependencies. That's what Spark is. And by the way, this image is taken from a book called Learn in Spark from Database. Highly recommended. So imagine that each of these pages here are documents. In Spark terminology, they call partitions. Right? Something is containing a collection of. Now, let's say I want to do this operation with column. Okay? I simply want to take a column as strings. I want to capitalize it to another column. That's a single operation. I can do that operation purely with the data just sitting in this document. I will have to do it in parallel across all three. But at no stage do I need one document talking to another. That's a narrow transformation. They are all properly chained when it's lazy. But the minute you want to do a join, right, like we said, it needs data from the other places because the key might match. A join is an example of a wide dependency. So yeah, if you have wide dependencies, you're going to cause a stage. Now the trick is sometimes you basically have to look at your code, figure out how many transformations you have, or rather how many stages you have, and you have to try to reduce the number of stages. Sometimes that happens by converting wide dependencies to narrow ones. Sometimes it happens by moving narrow dependencies that have narrow transformations that happen at the end a little bit to the top. Okay? We can talk about some of those techniques a little later. But the key is being able to identify this. What's narrow and what's wide. And once you have it, you need to know why is Spark treating it as a wide. Then you can go back to your code, see, you see the link. When you say join, you're going to see a new stage. And then we can talk about ways to maybe get it over. Okay. So I'm hoping the question is fully answered now. Cool. So yeah, how does Spark know what's lazy, what's in a single space? Anything which can be done in a single pass. So in the Spark example, in the word count example, if I have a sentence, I want to split it to words, capitalize, three operations, but all operating on the same record. Yeah, just merge them together. Anything which is wide is going to result in a shuffle. Like I said, shuffles are, I guess, the biggest issue right now in the D ecosystem. I don't think there's a way around it this yet. The best we can do is make them faster, less frequent, things like that. So avoid them at all costs. That is my advice to you. Yeah, this is an example of some Spark code. This actually is code in Scala, it's not in Python. That explains some of the fancy syntax of the dollar there. Right? So I'm hoping we can do a little exercise. We've spoken about transformations, spoken about actions, narrow and wide transformations. Can someone help me identify whether what this is? Which of those four operations is it? Read or state. Sorry? Action. Transformation. What makes you say that? Because at this point, I don't even have data about that. So to get it from here to there, all transformations are something that, this example, the arrow is invisible, sorry for that. But the definition of transformation is something that takes a data frame, returns another data frame. At this point, your code is just starting off. You don't have an input data frame. So you can't start transforming stuff until you have that first data frame. That's why the first read is an action. Yeah, same way. How about this one? Dot show the last line. Action, yeah. Because that's the point at which all your lazy evaluation ends. The dot show is similar to your printf, right? It's a function which doesn't return anything. It triggers an action, it prints out everything on your screen. There's no way you can make that lazy. You have to print the data task. Therefore, it's an action, it will cause all of this to get evaluated. Now, this is a nice fancy syntax. Okay? It's got three operations in the middle. Now, basically, what I'm doing is I'm reading the file, I'm removing all lines that have the word cat in it. Okay? Anyone want to tell me what this is? Transformation, wait, narrow, right? Okay. All three of these are narrow transformations. So the first one, there's filters of lines, which means it's a single operation because I read a record. At that point, I know yes or no, whether I want it there or not. I don't need to care about the data in the other records. That's why the filter is a transformation. The width columns, by the way, if anyone wants to talk about what these Spark operators do, just let me know. But basically what it does is it adds two more columns and then it expands the number of rows to split the sentences into individual words. Again, each thing depends just on the data and its own record, doesn't care about anything else. So all narrow transformations. How about this one? Why? Why? Yeah, so it's not possible to do this unless you need to know the list of all the keys. Okay? You need to know what are all the unique explored ones, which means you have to talk to all the partitions, figure out the key, and then you have to merge them all into one set. That's why that one is white. How about this count? Sorry. In this case, right, you can think of this as this count. This is actually Spark's own fault. Right? Their API is a little confusing at this point. Let's say you had a data frame object and you're doing data frame dot count. That's an action. You're going to read all the rows, you're going to print out the concept. But if you are writing word count in SQL, what's that query would write? You say select count of word group by word. Okay. The count here is that one, the SQL query. But it's not the one which counts as the whole mean. And the reason it differs, now this is a little bit of Spark internals again. But up till this point, all the width columns, they are transformations that read the data frame, return another data frame. That's actually why this dot syntax works. Each method here returns another data frame. So I can change them altogether. But group by, so different beast altogether. It's still a data frame, but there's so many new operations you have to do on the group by, right? You have aggregations, you have counts, few other fancy things. So the type actually changes a little bit. It's not a data frame anymore, it's something called a grouped data frame. So it gives you everything a data frame has plus a few more. Count happens to be one of those.
I don't know if this is valid. The dot count is going to give you a count in each category, the group by aggregated.
It will give you the count in each. So basically, this is shorthand syntax for using this syntax. Right? After you group by, you should say dot with column count comma count of exploded word. That's the full Spark syntax. This method is like an alias for that because you do counts on groups so often that Spark decided to give an alias. So for me, it was muscle memory. I did realize it would cause this confusion.
If I do count, dot count, can I, if I do another dot count on the count, that's the action.
That's an action. Because at that point, the alias has stopped working. And then dot count will actually evaluate. And yeah, this is actually valid Spark code. This code is the one that resulted in the DAG I showed in the previous page. So now you know what that filter was about. That was removing the word cat. So these are all narrow and ordered by last one. Also by super because you can't actually sort unless you know what other counts are there. So this lovely code actually results in three shuffles. While it looks nice and clean, there's a lot of problems with it.
So,
Hmm.
trying to understand the meaning of page development. A lot of these.
Yes, none of these operations will run. But at that point, all you have in your hand is a data frame object, which won't have any data in it.
So technically, that last action is not there, then read is not there.
So read has to happen earlier because it won't read the whole data. So if I'm giving it 5 terabytes of CSV, absolutely, it's not going to read all that. Yes. But there is some information Spark needs to have. Number one, the schema. Right? The minute you do dot read, it will first go check your data frame and it will figure out what schema you have, what columns you have, what types are those. Okay? That's base information it needs to have in order to support everything else and provide some safety. So read alone is like partially eager evaluation in terms that it will get you the schema and create a data frame object for you. But you are right that it will not read the whole data. Now, trick question. If it doesn't read the data, how does it know the schema? I just said that simply having this Spark will not read all the data from this. I also said that doing this will tell you the schema. It's going to tell you what kind of data you have, whether what columns you have, what's the data type of those columns. How can it do all that if it's not reading the data? What metadata is a CSV file have? Headers. Headers will, okay, so it has to read the file, no? First line. First line will just tell you header is missing. Does it tell you types? He is actually right. So depending on the file format that you choose, right? Let's say it's suppose a lot more. Anyone here heard of Parquet? Yeah. So Parquet is a file where it's a format which lets you store data and metadata separately. You'll have a little section at the top which says these are the columns I have, these are the data types. It will read just that part of all the Parquet files. But CSV doesn't have that. Spark still needs to guarantee everything. How does it do that? It randomly reads a few lines here and there in your CSV files. So if you have 4 terabytes, it will sample maybe 40, 50 lines in that file, figure out the schema by looking at those data points. And this, by the way, is a config in Spark. You can tell it what's the max number of records you want it to read to figure out schema. Because this is also performance rate, right? The risk you're running is that, let's say you have null columns or 1 or 2 rows are misleading. It might give you a wrong schema by looking at those few rows. That's why it tries to sample a bigger number. It can make sure the schema is more consistent. This reduces the probability. Okay, so that's one of the, how can you say, gotchas with using CSV data.
Earlier, you said cleaning the data is also part of it.
Correct.
So when you are cleaning, you might enter after there might be some impure data. The Spark cleaning on every time you.
So at this point of time in this code, when I'm doing Spark read, I'm asking Spark to tell me what is the schema that I have that time. So it will go through it, it will figure out something out. Let's imagine you have some dates in your CSV. Some rows, the date is missing. It's an empty string. So if it samples just the empty rows, then it's going to say it's an empty string or null. If it samples something else, it's going to say it's a date. If it samples both, it will say it's a nullable date. But imagine it had a date column, but your data is wrong. So date it had some ABCD. Now, depending on whether Spark saw that row or not, either it will say it's a date or it will say it's a string. Right? Because strings match everything. ABCD also gets matched. So at this point, you have to be careful. You can actually cast columns, right? I think that's an SQL feature as well. You can cast things from one data type to another. Same way, you can cast columns in Spark from whatever you read to a new type. If you had ABCD, the minute it sees that record, it's going to error out. Or another thing you can do is, in this instance, Spark.read, there are options. You can say, you can provide a schema, you can provide things like headers and other stuff. So you can say, this is my expected schema. I already know what the data is going to look like. I'll pass it as a parameter to this read option. Then when it checks the schema, if it doesn't match, it will error out there itself. It will give you a nice, beautiful error message. It won't let you proceed. So now you know there's something wrong that you have to go figure out.
I'm asking if there is a way to skip those nodes.
Skip, I'm not sure Spark is that as a default function. The way I've done it in the past is read it as a plain string. Right? It's whether it's date or ABC, you read it as a string, filter out nulls, then cast it as a date. When you cast the Spark, you can tell Spark to filter out anything that isn't a date. So we're moving to a slightly different section. So far, all good. Anyone want to ask any other questions? Okay. So we've spoken about evaluation and getting in there, but for all of this time, it has been about how Spark does things internally, how it builds this gap. We're going to get to the next part. Now that you have a dash, which is like, it's still metadata at this point. Nothing started executing. Now someone has to actually go read things from the disk, get it into the format way, write it out again. Okay. How does Spark achieve all that is the next section. How does it actually run? So I actually gave a hint about this earlier. If you have 50 terabytes of data, but your machine has only 16 terabytes of RAM, can it actually process all of it in one shot? No, right? Because it's all in memory. So it needs to somehow partition the data. Now this partition happens to be Spark terminology. Given a set of, let's say, a big piece of data, it will actually partition it into smaller pieces, right? And it will execute each partition at a time, all the operations in parallel. Now, if you have 50,000 files, 50,000 partitions, and it's going to start executing, but you might have just 5 or 6 executors. It can't do everything. That is fast forward. It will schedule all of them sequentially, let it finish, but it will not go to the next page until all the tasks are done. But to get there, it needs to know how many partitions are there. Because if you think about it, this also defines your concurrency. If I have, let's say, 200 machines, each with 4 CPU cores, let's say 800 CPU cores, and I have 10 partitions, what do you think will happen? Only 10 partitions will do anything. The remaining 790 will just sit idle. So you always want the input partitions to either be equal or greater to your partitions that your machines can actually handle. To do that, you should know how many partitions there are. So if think about this from Spark's perspective, right? You're asking it to read some CSV file. Or by the way, this doesn't need to be a single file, it can also be a directory which has multiple files. That I think that's the example I provided here. If I'm saying Spark.read data, data is a folder which has 10 different files. How is Spark supposed to know how many partitions are there? Any guesses? That's it. Very nice, very simple. So looks at the folder and says, okay, this guy has got 10 files. I'm going to do 10 partitions. That's it. So that's the first thing. Now let's think about how many output partitions there are. Input we just said is straightforward. Output is it already straightforward? In this case, all I have is one narrow transformation, two narrow transformations, and then an action. Right? Now, by virtue of narrow transformations, every partition depends only on its own data. So I can read a partition, finish the process, write it. That's why 10 input partitions means 10 output partitions. Let's take a look at the next two examples. This is a group by and join. Now we've spoken extensively about shuffle operations. So how many output partitions will be there? What if I have 10 million bytes? Okay. So Spark cannot leave things to chance like that because one more thing all of you should realize is it's a cluster, right? It's a distributed machine. And in Spark's context, it's not like there's a forum. The way it works is through a master slave kind of technique. So there is one driver node who has to keep track of all of this. He has to know how many partitions there are, if you're doing group by how many keys there are, which partitions are sitting in which executor. All that information the driver has to maintain. So you give it 10 million keys, that's a great way to get your driver to run out of memory. And that, by the way, is one of the performance issues you also see. You do have to do group bys very often in real code as well, and there's a very real chance you'll have 10 million keys. So that happens, your driver doesn't have enough memory, it's going to crash. You will have to make sure your driver has enough memory to handle all of that. If the driver is the one piece of Spark, it is not horizontally stable. And that's why they've kept it to a minimum that there is still some things that it has to have. So to answer the question, output partitions, it can't depend on data, right? It has to be hard coded. The way that works is there's a config. You tell Spark that whenever you're doing a data shuffle, how many partitions you want. It's something that you set in Spark when it boots up. It's called shuffle.partitions. That's it. The default is 300. So whenever you see a group by or a join and it has to shuffle data, 300 partitions is what it will shuffle it into. Assuming that you have at least 300 records. Less than that, well, partitions will be empty, so it will just be that number. So yeah, that's the answer. It will split it out into 300 partitions the minute it sees the shuffle. So it will read data as 10 input partitions. The with column and other operations as well will work fine. The minute it sees the group line, it starts evaluating, past the lazy stage. Whatever data it had will get split into 300 partitions, if that's the value you set. And your output is going to have 300 bytes. Because each partition is one byte factor of right there. Now, there is one gaping hole in this logic, one big performance issue. Any guesses? Yeah. So imagine a situation like this one. I made a very small change to the program, so I don't think it's visible to everyone. But what happened is this first file alone, 0.csv, it's gone from 40 MB to 10 GB. Spark in all its infinite wisdom, it's going to read that file as one partition. 11 GB is an insane number. Okay. Now imagine it's doing this operation with column upper right. All of these guys will finish their operation in 10 seconds. This fellow is going to take half an hour. Which means your entire cluster, the entire job is going to wait half an hour for it to complete. So waste of resources. If you could parallelize it, if you could distribute the data from here to there, life is going to be easier. So that's the next concept this Spark says. Even if it's reading file as an input, there's a max partition size. I can't remember the default, you can check the website. But the minute it sees a input which is bigger than that, it will refuse to read that partition, it will break it down. So in this case, it will actually split it into 11 GB by 10 MB, whatever that number is, get that many partitions. So if you were to simply do spark.read.this folder.write, no operations in it, just read and write. Because it can't read those partitions, your output is not going to be exactly the same. It's going to have as many output partitions as it wanted. So how do you change it? We said 300 is the default. It's not going to work for every job. Right? Your single cluster is going to run so many different jobs. And most of the time, Spark doesn't know better. It can't automatically figure out what is the right partition number. So you have to manually partition. Sometimes, in this case, there's a few edge cases. I don't think we'll get time today. But there are some cases in which Spark is not capable of splitting this automatically. The docs and that book I mentioned running Spark talks about it. So at those times, you will have to read all the into memory and then repartition. So it's basically left to the user to figure out what's the right partition number. And that is kind of the reason it's so difficult. You have to know your data very well, you have to know what Spark is doing. And even after that, it's basically trial and error. Figure out a good number, you test it, see how it goes, change it as required. Yeah, the last bit of today is data skew. Data skew is actually what I showed here. Right? Or it can be even worse. Let's say you're doing a group by and instead of a count, you're doing something on top of the groups. If there is some word which occurs 5,000 times more than any other word, whatever node, whatever partition contains that record is going to struggle. It's going to take a lot more time than the others. And the best way to fix it is to rebalance, to repartition the data into different nodes. But how do you as a developer know that there's a problem? That's why this is a screenshot of the Spark UI. It's called the Spark history server. When you run jobs, it basically gives you like a list of all the running jobs. It will tell you what's the stage of each job. And this section, I'm going to just focus on duration, the first record, first row. You can see in this thing, it completed 663 tasks. In my example, this is actually the one for the workout code, which I showed here. 663 is just because 10 GB got split. So that's the number it ended up with. Okay. Out of 663 tasks, the smallest of them all it took 1.6 minutes. But the max 5.5 minutes. And you can see there's a decent range. Like the median was 4, max is 5. Now this is not so bad because it's a triangle data set that has very but you do have cases where min can be 30 seconds, max can go all the way up to 1 hour. Okay. Those are also things that you see. But now the only way to know it is to watch out for this in each stage in your DAG, figure out where there's a skew, and then try to address it. There's multiple ways. You can filter out useless data, you can do the join a little earlier, or you can get rid of the join operator. All of those things will help you. So yeah, that's the thing at the bottom. Rebalancing partitions will improve your situation. But rebalancing means automatically that's in you all want to avoid. So I have to take the trade-off. You have to decide what's more painful, waiting this long or just doing this one. Any questions? Because it's a function of your data, not a function of your code. Spark can't figure it out until it sees the data you're operating. Yes. So this Spark operation, the Spark of read rate, it also has a backward part, which lets you set context. But you have to set it before you read. After you read it, it's not going to be existing data set only once. Obviously, four GB RAM, 4 CPU cores, and you set the part. In your example, you are running off a single computer. So 16.5 is going to be 16 partitions. But like you said, Spark cannot process 16 partitions at a time. You've got 4 CPU cores and not 4 partitions at a time. So it's just sequential. It's going to read the first 4 files, map them into 4 partitions. If it is a straightforward write, it's going to proceed, move to the next. In case it's needed for a shuffle, it's going to do its operation, keep that data somewhere, move to the next 4. So the shuffle happens at the end of a stage, which means all 16 partitions have to reach the end before it can shuffle. So in your case, Spark is going to have to read 4 files at a time to do its operations, keep that intermediate somewhere in memory, then do the shuffle, proceed. Runs out of memory, work on. Then it's going to help out, it's going to say all fancy things, work at night because of memory shortages. I didn't know this. And overnight. Yeah, absolutely. I just happen to think Spark is more user friendly than Spark. You're correct, a lot of people still use it. In fact, I think AWS themselves still offer it. It's on the same offering as Spark. It's called EMR. So AWS and other clouds, they charge you on the basis of compute time. And they charge you for the number of instances you have, how long you have it. Most of the cases we've spoken about, because of map reducing limitations, the frequent writes to disk and the other stuff. Usually the overall time is going to be a little larger. So it will end up costing you more. But that doesn't mean there are no operations at all. It is still very much used in production. In fact, Spark itself does use map reduce internally for a lot of its operations. I think it's So congratulations, we are done. So I put up two QRs on the left one is just my contact if anyone wants to reach out can. The right one is required if you want to please connect to a feedback that is going to. And the joke about the did you provide feedback?